Our next speaker will turn now to the other half of this question. This is utilizing solar power for cryo depot. Mark Henley has been a future guy at Rocketdyne and at the Boeing Company for a number of years, and was a longtime participant in NASA's space solar power studies. Mark.
Thanks, John. And again, this was originally planned for John Fikes. I'm one of the co-authors. Joe is also a co-author, but there were many other people who contributed to this. Connie Carrington was closely involved. Seth was involved. And it was kind of fun. It's a look at how you make propellant out of water in orbit using a high-power satellite system. So I don't want to read through everything, but the general idea is that there's water in the solar system, and finding that can be very, very important in getting from one place to the next. This is both on our moon, on Mars, and in other planets. Mercury, for one, has water ice, it looks like. So this is a technology that can be quite useful. The next one is that our baseline here was LEO. We wanted to see a facility in LEO that would have water delivered from Earth orbit as a way to start, and and be able to use that water to make liquid oxygen, liquid hydrogen, both propellants, and the hydrogen might also be a thermal propellant as a monopropellant. The liquid oxygen is useful for people to breathe. We used an electrolysis system. There may be other ways to do it, but that's what we used. And we wanted to talk about how this can help new commercial markets. So the assumptions were, let's see, 500 metric ton per year. And that was really with one depot for a lunar or L2 mission, 2 depots for a Mars mission. I think that might actually be a misprint. I believe we had 2 years of operation of one depot for the Mars transfer. But we needed to produce 500 tons per year. The water delivery options, we had a few different ways to do it. And in fact, at the time, there were people studying a gun launch of ice capsules into LEO. That was another way to do it, as opposed to a propulsive launch. And it was an equatorial orbit to simplify things. This was so we could have repeated launches again and again. And in fact, that was associated with the railgun launch concept early on. Low altitude, and with an equatorial site, we could access it every hour and a half. It wasn't like orbits at higher inclinations where you access them once or twice a day. That's it. We'll move to the next. A few different places that a depot could be, and objectives it could fulfill. Refueling spacecraft to go to transfer into GEO. Transferring out to the Earth-Sun L2 point for astronomy and other reasons. To the moon, of course, and onto Mars. Those were the drivers. This is the general scenario. There's a launch on one kind of vehicle or another that delivers a capsule full of water. It's a very dense payload. It's something that's safe and can carry high Gs. It's not a very sophisticated payload. That's carried to low Earth orbit with a orbital maneuvering vehicle of sorts that maneuvers, docks with a facility in low Earth orbit, and then in this case, number 4 there is the expended tank that either gets deorbited or sent back home. And then you can see as you follow the rest of the numbers, you have eventually a orbital transfer vehicle that gets refueled at the depot and takes a satellite out to, let's say, to GTO or other locations. To go through a couple of approaches here for settling, we just looked at ways to settle propellant either by rotation, centrifugal force, gravity gradient, which is also partially a centrifugal force. That is, you have one rotation as you go around per orbit. And sun pointing, which might help for solar power production, avoiding gimbaling arrays, things like that. And these were concepts that were related to those approaches. So we had a spinner that would settle propellants by a strong acceleration field, a rotational centrifugal force. A gravity gradient concept on the left was pretty interesting in that you could, we found a way to launch that whole, each one of those stacks is a single launch. But we kind of ended up with another gravity gradient concept which was a little bit smaller, and will carry these modules as upper stages that then are used as propellant tank sets in orbit as part of the depot. This describes the design a little bit further. It shows fairly large arrays on each side. The arrays of, they are arrays, but the lines of many propellant tank sets are set up to have a fairly low drag. They are in a gravity gradient orientation, and you have the hydrogen settling both away from the center of mass downward and upward, the hydrogen being the red tanks and the oxygen being the green tanks. And again, there are places for the water to be delivered at the docking ports, numbered 5 in that diagram. Okay. In this circle, you'll see the body-mounted radiator, and in this case, it was there to perform a couple of functions. One of them was to get rid of the excess heat from the propellant production, and another one was it would help in the orbital debris protection, that it acts as a bumper, as a shield to help protect against orbital debris. So I'm not sure I want to go through every element here, but one of the points was that with these large diameter tanks, these were 5-meter diameter, the surface tension was not so great that we had the surface tension did not cause the propellant to creep up against the walls very much. We wanted 5-meter separation from the CG for the oxygen, and a little more was necessary for the hydrogen, but that was sufficient to settle the propellants in LEO. So I think we're on chart 11, and there are about 30 of them, and I want to get through everything, but this was a picture of the configuration about how much propellant we had, and I think we ran it at 8-to-1 ratio rather than a 6-to-1 ratio, because that's the kind of ratio of oxygen and hydrogen we produce by cracking water. Showed a few different alternative thermal radiator configurations. The baseline, and this was some of the analysis of how that would be, what the temperatures would be on the system. Thermal assessment of different locations. And this was I mentioned that the radiators are important also for micrometeoroid and orbital debris protection. It turns out that orbital debris really comes from the sides in LEO. It doesn't come from below very much, sides and forward. So that is the area you want to protect from. The numbers in the boxes, I think, are the estimated chance of no penetration in a given year with a certain single shell, a single sheet of aluminum. And the thickness, typical tank thickness is about the 1/4 inch thickness. The exposed area we had was large, 100 square meters, and we had a chance of no penetration of being 66%. So it really has a 34 chance of being penetrated, that design, every year. And the issue is that we have to design the system smartly to prevent orbital debris from penetrating the sides. And by putting the radiators there, that help do the trick. This is a picture of a NTEC stretched lens array. This was again developed as one of the technologies in the Space Solar Power program. It was quite efficient, and it's what we baselined as the one that was to be used. Oh, I know that pin. There's a line here of solar cells, a linear Fresnel lens that concentrates the sunlight onto that line. This ends up being a very light and efficient configuration. So, now to get into the electrolysis situation, we have water coming in. It goes through a preheater in order to get it ready for electrolysis. We bring the temperature up from up to standard, and we pump it with very little power into the system. Go through electrolysis. This uses most of the power. We have 500 kilowatts in the electrolysis of the system, and not that much energy radiated. It ended up being fairly efficient. This was the system that the designers had. So to go on, there's a pre-cooler that chills the gas, and there's not much energy used there. Some radiated away. Here, where we go into a cryocooler for either oxygen in green or hydrogen in red, we use quite a bit of energy. In this case, it's 55 kilowatts, and most of that is lost. It's it's lost in the radiation of the system. Some of it's lost in other mechanisms too. But we use a fair amount of energy for cooling, as well as the majority being in electrolysis. And this is the other point I wanted to make, that we have quite a bit of excess of oxygen produced. In this system, we had 300 kilograms a day excess oxygen. So I think John smiles too. We suffered through a lot of these different charts in technology planning, and there was a series of challenges and different concepts that we went through, objectives that we tried to meet, and the different major systems, and the large-scale goal. In this case, it was delivering propellant as needed. Moved through a very simple chart that showed ground demonstrations of the technology. What do you do to make it more efficient? How do you, are there alternatives to electrolysis as ways to break water and get better efficiency out of it? What about the refrigeration? Cryogenic refrigeration systems are also fairly inefficient now. And then this one, I think, shows as an example, I think this one's a proton exchange membrane type fuel cell. But other things, we move into technology flight demonstrations. These might be secondary flight experiments, for instance, on upper stages. They don't have to necessarily be dedicated, but there are ways to demonstrate this in orbit. And then going into larger scale systems, demonstrating the components before getting into real commercial type facilities that would refuel stages for moon and commercial satellite deliveries. So to summarize things, we found that it was feasible to produce water in LEO on a repeated basis. It avoided some problems. The water is very dense compared to hydrogen and oxygen. The safety issues, it's not, there's no real issue in sending water to orbit, and we can allow very high acceleration if we want with ice or water. The same general system could work if you were to send capsules of ice from the surface of the moon into a lunar orbit. And that would be another way to make propellants in lunar orbit if you have something like a mass driver and a facility like this in lunar polar orbit. So we used a lot of different technologies to do this. It was space solar power technologies in particular, having a huge satellite system. This was an intermediate step in the use of very large satellites. And before you may have enough power to beam it to Earth efficiently, you have enough to do some other useful stuff. So that's about it. There should be other variations. I mentioned lunar orbit in particular. That it's possible to make systems that are smaller, but how do you make propellant at other locations, the L points, and we need to focus on some of this near-term technology for surface-based propellant production as well. There's not a lot in this paper, but it was quite important to be able to produce propellants on the surface of the moon, as well as being able to produce it in orbit. That's about it. John, you can guide questions as you like. Okay,
The tanks, have you considered the space shuttle external tanks for those?
I don't think we really looked at the space shuttle external tanks. They were fairly big at the time to make something up incrementally. In fact, I think we ran through what there was that was available. I think we wanted 500 tons or so. So the shuttle tanks, I think, were actually too big. That was my memory. So maybe something you might correct me.
That sounds right. Also, although it's not a major thing, the shuttle tanks are sized for 6-to-1 mass ratio.
Yeah.
So that would have to be modified.
Either modified or...
I think there were issues with the spray on foam insulation.
Was there another question to that?
Oh, is this available online anywhere?
I don't know. I don't know if John's put it on online yet.
It could be, not at this point in time, no.
Well, it must be some DVDs.
Yes.
Do you think it could be economically feasible to take blocks from the moon and store it in your depot for like boosting, for geotransfer stages for commercial vehicles or something like that?
That's a pretty good question. Do I think it might be economically feasible to have blocks from the moon and store it in a depot? And I believe that yes, it may be. That there can be ways that it might be easier to get propellant from the moon and water from the moon than it is from Earth. That is, it's kind of it's conceivable that you can take water and launch it and aerobreak it into low Earth orbit as a package that's delivered and then process it. As easy as it is to get propellant to L1 or L2 or any of those points, it's almost as easy to get to low Earth orbit as you can make an aeroplane also. If you just make oxygen on the moon, I mean, certainly that can also be done too, but then you need the hydrogen from some other location. And we already have access to oxygen, so I think it's a greater advantage if you make both propellants than not just the last one.
I was thinking in the context of you integrate it with like the cargo vehicle that Joe was talking about. If it's taking stuff out, it could also take stuff back. Move back and forth and integrate these ideas.
Yes, I think that's probably.